understand the things more properly and revise the class notes. That is the most important. That is the first step. Understood? Whatever we are doing it here,
Understood.
you should once after ending the class. What do you used to do after ending the class?
Nothing. Like I just read through it once,
You,
quick. Just read through it fast.
sorry, I can't understand. What did you say?
I just read through it quickly, like the main
Okay,
headings.
you read it quickly, but read it slowly. Okay,
Yeah, yeah.
so
Right.
that you should understand each and every topic, whatever was being taught there, and try
Yes.
to do at your own. For example, if you had seen a particular diagram, for example, we had kept the two charges, we are finding the force on the third one, you got the aim that we have to take two charges and we want to find the force over this. Now try to find the force by yourself, okay? Not by looking at the notes. You had already seen it once in the class. Now try to do it by yourself. Once you get stuck at any particular instant or any particular point, then look into the notes that what was being done there and what where you are lagging behind. Okay. And if somehow
Okay.
you don't get an idea that how you have to do that, do it look at the notes and do it completely once after seeing it. But once you had done it, just close the notes and again do it by yourself without looking the notes. Okay.
Okay.
The more you will
Okay.
practice, the more you will get the clarity over this. It's not a task of 1 day or 1 hour or 2 hour or 2 day or 1 week. You have to do it continuously. Only then you can do good in this particular field. Okay. Otherwise,
Okay.
just by doing it once or doing it twice will not make you understand. Will It's not possible for anyone. Okay. So you should
Okay.
do it uh, uh, again and again. Then only you will master it. Okay.
Okay.
So should we start our next class? What we were discussing in the last class? Do you remember about it?
Like it was derivatives, like axial position, equatorial position.
Yes, we had seen for the particular dipole. Okay. After that, we had also
Mm.
seen that what happens when a dipole is being kept in a magnetic field, uniform electric field. Yes or no? Have we seen that?
Yes. Yeah. Yeah.
Have we seen that? Yes or no?
Yes. That.
What happens when a magnetic field? What is the net force over that particular dipole? That is zero. Do you remember it?
Yes.
The
Yeah.
force is on the plus charge and minus charge in the opposite direction. So the net force is zero, but net torque was not zero. That particular
Mm.
system tries to rotate. Yes or no?
Yes.
Have you seen
Mm.
that, or can you see it in your notes that it tries to rotate? And then we had also
Rotating
found out the torque over that particular what we say torque over that particular
dipole.
dipole.
Dipole
What was the torque there
is
that we had found out?
P into E. P into E.
P
Right.
into A. Is that correct statement, or you need to write it correctly? What was the torque? Was that P cross E?
Yes. With vector.
That was P cross E. Okay. And if we need to find out the magnitude of this torque, what will I get? Magnitude of P, magnitude of E into sine theta. What
Yes.
does this theta stand for?
The
Theta is the
angle.
angle between what?
Two charges.
Uh, Between two charges.
Is it?
Angle between P and E.
P, P and E. Yes.
Yes or no? It is the angle between
Yes.
P and E. After that, we had found out the work done also, and all the things were done discussed in the last class. Yes or no?
Yes.
And before that, we had also calculated that what could be the maximum torque, minimum torque, like something like that. Yes or no? Do you remember all
Mm,
those things? Have you revised the last
where was
class?
ma where was the maximum?
Yes, all those things were there. Okay. Today, the
Yes.
topic that we have to start is not connected with this one. It is a totally uh, different topic other than this particular dipole. Okay, so no need to worry, but
Okay.
you should, I will recommend you still that you should remember, you should revise those things once more.
Yeah, I did. Okay.
Okay, okay, so our today's topic is, okay, so our today's topic is charge distribution. Charge distribution. Till now, what we had seen, that we had kept some of the point charges always. Yes or no? Initially, when we were discussing about specifically about the point charges, thereafter we had considered the two opposite charges and we had constructed a dipole. Yes or no?
Yes.
But now, what is going to happen? We are going to talk about that what will happen if we have more than one charge, that is a group of charges is being kept with us.
Okay.
Understood? That means charge is being distributed over something. Understood? Previously, what was
Understood.
happening, that we were talking about the single point charge. Yes or no? But now
Yes.
what I'm going to do, I'm going to distribute the charge over something. Okay?
Okay.
Understood? So
Okay.
what
Yeah.
we'll say, what we'll do, we'll distribute the charge over distribution of charge. We are going to discuss about the distribution of charge. So see, if we need to distribute the charge, what could be the possible things? Uh, I think the first thing that we can do, we can distribute it over a particular line. Yes or no? For example, we'll keep a single line,
Yes. Yes.
and what we'll do, we'll keep some charge over uniformly distributed over it. For example, let us take the plus charge. Yes or no? Can we do this?
Yes.
Yes, we can distribute this particular charge over this particular line. So what will be this called? This will be called line charge distribution. Yes or no? Because we
Yes.
are
Okay.
distributing it over a particular line. Okay, so this will be called as line charge distribution. Line charge distribution. Okay, understood? So instead of writing it here, I think I should, what is this happening? Yes, instead of writing it here, I think I should, yes, I should just keep it here. Okay, understood. So we are talking about the line charge distribution. The first thing that we are watching here is that we have distributed the charge over a particular line. Is this clear to you?
Yeah.
Okay, so this was the first thing that we had seen here. And what the second thing could happen, that we can distribute it over a particular surface. Yes or no?
Yes.
We can definitely distribute it over a surface. So what the second thing that we can do, we can, that we'll call it as surface charge distribution. Yes or no?
Yes.
Surface charge distribution. If we are distributing it over a surface, so let us consider any surface. Let us take as this to be a surface. Understood? If we are taking this to be a surface,
Yeah.
what we'll say, that the sign charge is being distributed somewhat like this. Okay. So this will be called the surface charge distribution. And remember this, that it's not need that not necessary to take only plus charges. We can take the minus one also. It doesn't matter. Okay, understood?
Okay. Yes, understood.
Yes. So it is called the surface charge density. What could be the second thing? Can you guess the second one? Where else can we distribute the charge?
Area.
We had already discussed about the area, line and area. What could be
Surface.
the one another type? Can we
Mm,
distribute it over a volume?
yes.
What do we mean from the volume? That it is embedded inside something. Understood? Like it is
Mm,
being
understood.
kept inside a particular volume. So that will be called as a volume charge density. That will be called as a
Volume charge. Yes.
volume charge density. And instead of saying the above as surface charge density, we should say it as surface charge distribution. I should say it as surface charge density. I should say it as surface charge density.
Density.
Okay. And the above one, again, we had said it to be a line charge distribution. We can say it as a line charge density. We can say it as a line charge density.
Density.
Okay. What I mean from the volume is that suppose let me draw a 3D figure here. Suppose we have somewhat like this. Okay. We have a volume somewhat like, can you imagine it that this is a 3D sphere?
A
Or,
sphere. Mm,
okay, understood. This is a 3D sphere. And what is happening
yeah.
here? Uh, Let me do something here so that you can understand more clearly. I think now you can imagine it in a better way. Okay, that part that is dashed in the dashed form, that is behind us. Okay, we are unable to see it. That's why I had made it with a dashed form. Is it clear?
Mm, mm.
Okay,
Yes.
so what is happening here? That the charge is inside the volume. Charge is kept inside the
Inside the
volume.
wall.
It is kept inside the volume. So what will you say it as a volume charge density? Okay, is this clear to you? Now,
Yes. Understood.
can we write something here? Suppose what is happening that uh, this total amount of charge, this total amount of charge is Q distributed. Q is distributed over a length of over a particular length of L. So what will I say? I'll say it as a line charge density. We generally used to represent it with the lambda. We use lambda for to represent it, and that will be called as Q by
Mm.
L, charge per unit length. What it is called?
Charge per unit.
Charge per unit length. Understood?
Okay.
And if I'm talking about the surface charge density, suppose we have a Q charge distributed over the area A. I can define the surface charge density as Q by A. Yes or no?
Yes.
And we used to represent it with sigma. What this will be called? This will be called charge per unit area. This will be called charge per unit area.
Charge.
Understood?
Area. Yes.
Now see, the next one is the volume charge density. So can you guess that how we can we can represent this particular thing?
Q by V.
Yes, exactly. That will be Q by V. And what it will be called? It will be called charge per unit.
Volume.
Yes, charge per unit volume. Understood? And it is generally represented
Yes.
with a quantity rho. Is this clear to you?
Yes.
Now, the good thing about after doing so is, suppose we get a line charge density as lambda, okay, and we need to find out the charge on charge on dx length. We need to find out the charge on dx length. Can you understand that dx? I mean that it is a very small length. It is a very small
Mm.
length dx. I
Right.
need to find out the charge over that. So what I need to do, I just need to do that charge, that small charge dq. Let us consider that that is a small charge, that is dq. That will be called as lambda into dx. Can we
Yes.
say this? Yes or no?
Yes.
Because
Yes.
charge per unit length is lambda. So charge on a dx length will be lambda into dx.
Yes.
Yes or no? So we can say
Yes.
this. The similar things, can you write it for charge on a dV volume? Not charge on a dA area. We in the second case, what we'll do? We'll take a small area dA. We'll take a small area dA, and we want to calculate the charge over that. So what will we do? Charge over dA volume. So what will be the charge on dA volume? That will be. Do you believe that small charge dq will be sigma times of dA?
Yes.
Yes
Yes.
or no? Because
Yeah.
Q charge is the sigma is the charge per unit area. So on the small area dA, the charge will be sigma into dA. Yes or no?
Yes.
Similar thing, can we do it here also? That charge
Yeah.
over dV volume. What will be the charge over dV volume? Can we say that a
Oh,
small charge
into
dQ will be rho into
DV.
dV? Exactly. So now I think you are comfortable with this. Understood?
Yes.
Yes or no? So these are some of the very important things that you must remember about. Is this clear to you?
Yes.
All okay? Is there any doubt in this particular thing? So you must ask it now only.
No, I understood. Yeah.
Okay. Okay. One, it's a very common thing, but I must write it here. What will be the unit of lambda? What will be the SI unit of lambda?
Coulomb by meter.
Exactly. No issues with this. What will be the unit of sigma?
Coulomb by centimeter square.
Coulomb by centimeter square. What is the SI unit of area? Uh,
Meter square. Okay. Yeah. Yeah.
okay. Hmm. Why is this option coming to? Okay, and if we talk in the third case, what will be the unit of this? That will be,
Coulomb by meter cube.
yes, exactly. No issues with this. Have a confident in answering all these things. Okay, understood? So these are the things that
Understood.
we must know. It's a very easy thing, and I don't even believe that I should discuss it here. But as we are discussing about it, that's why I just discussed it over the unit also. Understood? Is this clear to you?
Understood. Yeah.
Okay, now the next thing that we are going to do, why I had told you about this, we are going to use this in that particular thing. Okay, the next topic that we are going to start is electric flux. The next
Mm.
topic that we are going to start over here is, understood. Uh, Let me write it. Just a second. Okay.
Mm.
What happened? I think I should rejoin. Something happened here. Okay, I'm rejoining that.
Okay.
No, I think. Okay. So can you see it now?
Yes, yes.
Okay. We were talking about the electric flux. Okay. So see, uh, flux can be of anything. Understood? Flux can be of anything. It could be electric flux, it could be magnetic flux, it could be flux of water also. Okay. So we have but the thing that how we use to calculate the flux is the same for everything. What we need to do, we need whenever we are finding the flux, for example, we are finding the electric flux. So I'll give you the example with this only. Okay, let's not take this. Let us assume that there are electric fields like this. There are what are there? There are the electric fields aligned somewhat like this. Okay, so what I'm drawing it here, that we have the electric field somewhat like this. And let us take one more. Okay, so we have the electric fields, uniform electric field is directed somewhat along this. Now, and what else is here is that we have a area that is somewhat like this. We have the area somewhat like this. Okay, and we want to find out the flux through this area. What we need to find out? We now need to find out the flux through this particular area. So see, whenever you need to find out the flux through this area, so what you have to do, you for finding out the flux, you need to multiply the electric field and area in direction of electric field. Actually, area perpendicular to this electric field is the correct word. Electric field. Okay. And if we need to do this, what actually is required here? See, suppose we have a area vector aligned along somewhat in this direction. Okay, understood? We have
Yeah.
the area vector in this direction. So what is happening? It is making an angle theta with the E. Yes or no?
Yes.
Okay. So what will be the phi E? That will be E dot A. The reason behind that, see, actually what I had said to you, that we need to find out the area that is perpendicular to the electric field. So you need to take the component of A along E. And what will be the component of A along E? That will be A cos theta.
Okay.
Yes or no? That will be
Yes.
A cos
Because
theta. Can you see this? That this component of A will be, that will be A cos theta. Is this clear to you? So what will be the
yes.
E here? The E will be the phi E, that means the flux will be E into A cos theta.
very good.
Understood? So basically, what you need to do is to multiply the area that is perpendicular to this particular electric field. Okay, is this clear to you?
Could you repeat that line? No.
See, whenever you need to find out the flux, you need to see that
Yes.
how many electric field lines are passing through that particular area.
Okay.
Okay, so actually, once I'll give you the example, then you will more clearly understood this. Now see, how we can replace this. What we can do phi e to be e dot a, phi e to be e dot a. Can you see that E
Mm.
dot A will, if you will open this up, you will get the above expression only. E into A into cos theta. Yes or no?
Yes.
If we
Mm.
open A dot B, what do we get? A B cos theta. Yes or no?
Yes.
Okay. So now see, what I was trying to say to you is that suppose suppose what we are doing here is that okay. Now let me give you some examples here. Suppose what is happening that we have uh, what we are trying to do. Let us make some electric field lines. Okay. Can you see these electric field lines?
Yeah. Yes.
Is it looking like electric field line?
Uh, Rectangles.
Hmm?
Yeah. No.
Now are they looking like electric field line?
Yes.
Okay. So what we have suppose we have this electric field lines in this particular plane. Okay. Now what is happening here? Suppose that we have a area. Okay. Suppose we have a rectangular sheet. We have this particular rectangular sheet here. Okay, we have this particular
Okay.
rectangular sheet here. And what will be this sheet? Suppose that this is having a length L and this is having a breadth B. Okay,
Okay.
now tell me one thing, that as these electric field lines are somewhat directed along this direction. Okay, can you understand? It is from our left to our right. Okay,
Left to right.
electric field lines are from our left and going towards right. Yes or no?
Okay.
Okay, is this happening here or not? Like I had drawn it. According to this, what is happening? That electric field lines are going from left to right.
Oh yes.
Yes or no? It is going from our
Yes.
left to right. Now tell me one thing, that if I keep the sheet into this particular electric field line, so there are many possibilities that how I can keep this up. Yes or no? Because I can keep it
Yes.
in any way. I can keep it in any way. Suppose the
Anyway.
way I had kept it here, the way I had kept it here, do you believe that none of the electric field line are going to cross that particular area of this plane that I had drawn here? That this particular plane, what is going to happen? That none of the electric field line are going to cross this particular plane that I had drawn here. Yes or no?
It will come.
See, what is happening? That you had kept the sheet like this, and the
Okay.
electric field
Yeah.
lines are passing over this. They are not crossing this particular area.
Okay.
They will just pass from over it and will not cross this particular
Understood.
area. Do you believe this?
Yeah. Understood. Yes.
So what will be the flux? In this particular case, what will be the flux?
Zero.
That will be
Mm,
zero, because none of the electric field lines are passing through this. Understood? So basically, this is how you
understood.
need to find it out. Now tell me one thing, that if I keep it like this, see now you will be able to understand. Suppose I'm marking some point over here, A, B, C, and D. If I'll keep this sheet like this, see first of all see it, then you should write it. If I'm keeping it like this, and the electric field lines again passing from left to right, electric field lines are again passing from left to right. So do you believe that from throughout this area, the electric field lines are going to pass?
Yes.
Yes or no? And if I keep this
Yes.
into this particular scenario, what will I get? I'll get just a straight line. I'll just get a
Mm-hmm.
straight line. If I'll
Straight line.
keep it into this particular plane, you will just see that there is a straight line kept inside this field, according to the view where we are sitting right now. And what is happening here? That point A will be kept here, and point B will be just behind it. Yes or no?
Yeah.
And similarly, the above point will be point D,
D.
and the point C will be exactly behind it, and we will not be able to see it. Yes or no?
Yes. Yes.
So, and now in this case, what will be the flux? This was the first case. This is the second case. What will be the flux? That will be the electric field into the area through which it is passing. What will be the
Yes.
electric field will be E, and what will be the area this time?
L into B.
L into B. Yes, exactly. Okay, L into B. This will be the total thing. So can you understand that how you need to find out the electric field?
Mm, yeah.
Now tell me one thing, that as we had kept it like this, see, first of all, see it here, as we had
Yeah.
kept it like this. Now what I'm doing here is, I'm just rotating it. I'm just
Mm.
rotating it. It's still the electric field line is this. Now, do you believe that as you had rotated this particular plane, now it will reduce? It will not be this much E into LB. It will start reducing.
Yes.
Yes or no? Because the effective area facing the electric field will reduce.
Yes.
So basically, this was the thing that I was saying there, that what you require is, you require the area which is perpendicular to this electric field always. So
Mm,
now
no.
suppose
Yeah. Always.
initially it was like this, and the electric field was like this. Can you see it? Can you see it? That the electric field lines were somewhat like this.
Yeah. Yes.
Okay, electric field lines were somewhat like this, and it was passing through this. Now, as I had
True.
rotated it, so this complete area is not facing this electric field. A component of this area, that is a cos theta, is facing this particular electric field. See, I think now you will be able to see it, but I don't know that whether this will come into the camera or not. Okay, so suppose that this is
Okay.
the complete area. This is the complete area.
Complete.
So
Yeah.
what is happening? That initially this area was kept like this. So all the electric field lines were passing through this L into B. Yes or
Yes.
no? As I
Yeah.
had rotated it a little, for example, I had kept it like this, I had rotated it a little. Understood? As we had kept it bilkul vertically like this, in this case, the whole area was facing the electric field. As I just rotated it a little, what does this mean? That now the area facing the electric field will reduce, and a component of the area, that is a cos theta, a component of area that is somewhat like this. Understood? Perpendicular to the electric field,
Mm.
that will be the a cos theta. This is a, and the direction in this, that is the perpendicular to electric field, will be a cos theta if it
Yeah.
had rotated with an angle of a theta. Understood?
Understood.
So what will be the electric field in that case? That's why I had written the general formula of electric field to be E A cos theta. Because if it had rotated with some angle, then we'll see it as this.
Oh, okay.
Okay. As it is like this in this scenario, in the case second. Well, the area vector is also in this direction. Yes or no?
Yes.
Parallel to E. Now, as the area vector is in parallel to E, what is the angle between A and E?
Uh, 90 or less than.
What is it?
Could you ask the question?
See, if I had kept the sheet like this in the case second, I'm talking about this case.
Yes. Yes.
As I had kept it like this, so what the area vector will be somewhat like this, as I had marked
Yes.
here. So what is the angle between the area vector and E in this case?
90 degrees. Open it.
If E is in this direction and A is also in this direction, what is the angle being made between A
180.
and E?
180. 180.
E was in this direction, and what I
0
did
degrees.
initially, if A is like this, so it is making some angle. I'm reducing it to like this. Yes or no?
Mhm. Yes.
See, now tell me that what is the area between this rotating vector is the A. What is the angle between A
Okay.
and E right now?
90.
What is the angle between A and E?
180.
And what is the angle between A and E?
0.
Zero. Understood? So as they
Okay.
are in the same direction,
Understood.
so the angle between them is the zero.
0.
Is this clear to you?
Yes.
So basically, what so while finding the applying this particular thing, what will be the value of theta here?
0.
That will be
Is,
zero. And if it will be zero, so what is the value of cos zero?
1.
Yes, cos zero is one. So ultimately, did you got this thing only E into LB
Yes. Yes.
while applying this general formula also?
Yes.
Understood? So basically, that's why I had written this. Okay. Now tell me one thing that uh, let me do one thing. Let me make life easy for me. Okay. This is the example second that I'm talking taking here. And but now what I'm doing here this time is okay. What I'm doing here is that this time I'm taking the sphere. Okay. What it is? It is a complete sphere inside it. Okay. It is a complete sphere inside it. What will be the flux now in this case?
Electric field into
E into what is the effective
the area
area
of the
of this
sphere.
sphere that is facing this electric field? Suppose it is having a r. It is having
Hmm.
a radius r. So what will
Semi-sphere.
be the yes, it is a sphere. So how much area it is facing the electric field?
Um, Half of it. Semi-sphere.
Semi-sphere. Area is
Or
a
the whole
2D
sphere.
thing. Area is a
Okay.
2D thing. So you
Okay.
should not talk about the volume. We'll always talk about the area.
Area.
What do you believe that the exact thing will look like?
Hmm.
Do you believe that the sphere will be somewhat like this? in the vertical thing if I'm talking about.
Yeah.
So
So,
don't you think that a circle will be the area this time?
yes. Yeah. Okay.
This time a circle will be the area, and the area of that circle will be pi r square.
Yes. Well,
Yes or no?
yes.
Because that is the maximum thing that this particular sphere is facing. Understood?
Understood.
So what will you multiply here is E into pi r square. Understood? Yes or no?
Yes.
Now tell me one more thing. If I take another example, if I take another example, and instead of this sphere, what I'm taking here is I'm taking the, suppose what I'm taking here is I'm taking the, this time I'm taking this. Okay. What I'm doing here is that I'm just cutting this from the midpoint. Okay. What I'm doing here is I'm just cutting it from here. So if I'm cutting it over here, what will I get? I'll get a, what will be the figure will be called after cutting it from this point?
Hemisphere.
That will be called a hemisphere. So do you believe so that the obtained figure will look somewhat like this?
Yes.
And if it will look like this, now tell me that if this particular thing is being kept in this particular electric field, now what will be the flux in this case?
Semicircle.
Yes, that will be the semicircle. So E into pi r square by 2. Yes or no?
Yes.
Understood? Because now this time what is happening? That this particular thing, uh, this particular area, okay, that this particular area is facing this particular electric field. Understood?
Understood.
So this was the case while for a particular if I keep a hemisphere here. Now tell me one more thing, that if what I'm doing here is that this time, instead of that particular thing, what I'm doing, I'm just keeping this particular, okay, what I'm doing here uh, is it looking like a sphere? Is it looking like a cylinder?
Yes.
Let me draw it properly. Okay, so is it now looking like a cylinder?
Yes.
Now tell me, what if I keep this particular thing into this particular electric field? What will I get? What will be the electric flux now this time in this case?
Electric field into rectangle.
What is the
area.
effective area? Yes, that will be the rectangle. Exactly. Now you understood the thing.
Mm.
Okay. Let me make it again here. Okay. So what will I get here is, if I am keeping this particular cylinder into this particular electric field, that will be the rectangle. You got it correctly, that will be the rectangle. But what will be the dimensions of that particular rectangle? If it is having a height of, let's say it is having a height L, it is
Height
having a
into
height
diameter.
of L. Yes, exactly. You got it correctly. This is the thing. Okay. So, and this is the radius R. So, height into
Mm.
diameter will be the area in this case. The electric flux will be written as E into, now the it will write the area. What will be the area? That will be L into 2R, length into breadth. Yes or no?
Yes, yes.
Yes, this will be the thing. Now tell me one more thing, that now I think you understood it. Now you'll be able to do it correctly. Instead of taking, uh, oh, okay. Now what I'm going to do here is, uh, I'm going to take the cylinder like this, and I'm going to keep it there. So what will be the electric flux in this case?
Electric field into area of circle.
Yes, exactly. Now in this case, electric flux will be E into, okay, E into pi r square. Okay, and what type of electric flux we all are calculating here? We are calculating the flux that is entering. Okay, we are always calculating this entering flux. Okay, phi is the, I'm just defining the phi here. This is the entering flux. Okay, because there will be the flux that is exiting also. Okay, so I'm just talking about the flux entering inside it. What I'm doing here is that flux, it is the flux entering. Okay, I am I do not I'm not concerned about that, concerned about the sign here. Okay, I am not concerned about the sign here, whether the phi e will be positive or negative. I'm just calculating it, that what will be the magnitude. So I'm just calculating the magnitude over here everywhere. Understood?
Understood.
So that will be the case here. Now I think you got it correctly. Now you are good to go ahead. That now we are very much confident about while calculating the electric flux. Is this clear to you?
Yes.
So this was the thing, and let's move ahead. Okay. Now the next thing that we are going to start here is the Gauss law. Okay. These are all the electric field. Okay. The next topic that we are going to start here is the Gauss law. Gauss G. We are going to start the Gauss law here. So actually, Gauss had given a law. Okay. And what it is used for, basically, till now, what is happening, that we had seen the electric field due to a point charge. Yes or no?
Yes.
What was the that expression?
Electric field.
What was that expression?
F by
Due to
Q.
a point charge. Due to a point charge, what is the electric field?
F by Q, or is it the Coulomb's law?
Yes, what was that?
K into Q1 into Q by R square.
This was the electric force, electrostatic force.
Yeah.
That was force, but I'm talking about the electric field. Have we talked about that?
Yes.
What was that?
F by Q.
F by Q. Have we talked about something that if the point charge Q is kept here, so at a distance R, there will be the electric field that will be KQ by R square.
Yes. K
Yes
R
or
square.
no?
Yes, you have.
And when we need to know about the force between the two charges, Q1 and Q2, then we used to say that Fe equals to K into Q1 into Q2 by R square.
Yes.
If the R is the distance in between them. Yes or no?
Yeah. Yes.
So this was there. But so basically, and the second thing that we had seen the electric field due to a dipole.
Mm.
Okay, so basically we had done those two things, that we had seen the electric fields due to a point charge and uh, 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 due to a particular dipole. But we had not seen the electric field due to any other thing except these two. Yes or no?
Yes.
So, but now after learning this Gauss law, we'll be able to calculate the electric field due to some other things also. Okay, understood?
Mm. Understood.
Sorry. Is this okay to you? Yes or no?
Yes.
Okay. Let us, it's the radius r here. Okay, so what is actually the Gauss law says? Gauss law says that total electric flux linked with a closed surface is equal to 1 by epsilon times of charge inside the closed surface. What does this mean? This says that there is a surface we don't know about, okay, but if you want to calculate the total electric flux through that particular surface, phi e, understood, that we were calculating till now. Is this okay? If you need to calculate the flux, so that will be nothing but you just need to check that how much charge is enclosed inside that particular surface divided by epsilon naught. Is
Okay.
this clear to you? So first of all, I should write the statement here and then we'll move ahead. Okay, let me change the pen. It says about the total electric flux linked with a closed surface is equal to 1 by epsilon times of charge inside the closed surface. Understood? So what does it say about? It say about that first of all, it is calculating the total electric flux. Okay, it is calculating the total electric flux. And what it is saying, that suppose that there is a surface. Okay, let us, it is saying about that suppose there is a particular surface. There is a particular surface.
Mm.
And we need to calculate the total electric flux linked with it. Okay, we need to see
Mm.
that what is the total electric flux inside it. So what you have to do, you just have to see that how much charge is enclosed divided by epsilon naught. Is this clear to you?
Yes.
Is this okay to you?
Yes.
Okay. So phi E equals to Q enclosed by epsilon naught. This is the basic mathematical equation that we had seen or had drawn it. Okay, from this particular law. Okay,
Oh,
now see how we are going to use it. Do we have any other method to calculate this phi E?
electric field into area.
Yes, exactly. We have the one more method for to calculate this phi E. So ultimately, what we can do is we can do E dot dA equals to Q enclosed by epsilon naught. Can we say this? Yes or no?
Yes.
So this is the statement that will be very helpful for us while calculating the other things. Understood?
Understood.
Okay. So this was the basic expression that we are going to use over here. Okay.
Okay.
Understood? Okay. But
Yes.
uh, 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 the problem with this particular expression is you can calculate the q enclosed because it is very easy for us. For example, let us say that it is q1 minus q2. These are the charges inside this. Okay, let me write it with some different pen. Okay, let us say that it is having the charges plus q1 minus q2 plus q3 q4. Okay, q4 and minus q5, and let's say minus of q6. Suppose this is the total distribution over here. Now, if I say to calculate the electric flux through this particular thing, so what will you do? While calculating this, what will you do? That will be apply
Look
this
for
one.
chance.
What is the Q enclosed inside it? That is Q1
Plus Q2 plus
minus of
Q3.
Q2 minus of Q2. This thing you
Yes.
should
Yes.
take care about. This is
Yeah.
with minus sign. Minus of Q2 plus of Q3 minus of
Plus of
Q6.
Q3.
Should I consider the Q4?
No.
No. Why? Because it is outside the volume
Mm,
and we need to take the charges inside the closed
very
surface.
close.
Okay. So we'll not consider this Q4 and Q5 and whole divided by epsilon naught.
Yes.
Is this clear to you?
Yeah.
Okay to you? So now you are okay with calculating the RHS side in this expression. I'm talking about this particular expression. Okay,
Yeah.
you are good
Yeah.
to calculate the RHS side. But what is problem here? The LHS is the problem. What
Mm,
is the problem?
yeah.
You will not be able to calculate E dot dA every time. The reason behind that is, for example, let's say what I'm doing here, I'm taking a random surface here, somewhat like this. Okay, let's not take this. Let's take a good one also. And let me see. Okay, suppose what is here that we have
Mm,
somewhat the
Tube.
we need a closed surface. So we are taking this to be as a closed surface. Is this okay?
Yes.
We are taking this particular thing to be a closed surface. If we are taking this to be a closed surface, and let's say I'm keeping a charge here. Okay, let me take only one charge. Okay, although this is true for many charges also, but I'm taking as a one charge only. Suppose I'm taking this to be a charge. Okay, if
Okay.
you need to calculate the E dot dA, so do you agree that there are total how many faces are here of this cube?
6.
Six faces are there. That means you need to calculate E dot dA for the six faces. Yes or no?
Yeah.
Now one more thing. if I talk about the area vector of the above surface, do you agree that that will be aligned somewhat in this direction, perpendicular to the surface?
Yes.
If similarly, if I ask you to calculate the area vector for other surface, you can easily do it. Yes or no?
Yes.
I'm drawing only for the two. Okay. But now
Okay.
tell me one thing. If I find the electric field from this Q1, if this is a positive charge, so it will be leaving this Q1 or not?
What?
If this is the positive charge, so electric field will be leaving or entering inside this Q1?
Uh, Leaving.
Leaving, definitely. So if it is leaving, so let's say the first charge, the first electric field, that will be pointed somewhat along this area vector only. Yes or no?
Yeah.
Okay. But will there be only one or will there be many?
Many.
There will be many, because we had seen this while drawing the electric field in the previous sessions. Okay, so there
Yes.
will be one electric field that will be somewhat like this. And what will be the area, what will be the angle in between area vector and the electric field in this case?
0.
Zero. So you can calculate E, A, and everything. But if you are talking about any other area, then do you agree that you have to take the electric field in this direction? There will be electric field in many directions,
Yeah.
and not only one. There will be infinitely many.
Yes.
Like I cannot draw each and every one to be here. And for every electric field line, the area vector will be somewhat like this. So can you now calculate the area vector for all these small area that I'm taking here? Can you now calculate the angle between them? That will be somewhat, but we don't know about.
Yeah.
That will be somewhat, but we don't know about that what it will be. So do you agree, while calculating E dot dA, if you will apply the formula E into A, if you're taking the small area, so you will take dA into cos of this theta. This theta is not being known by you.
Yes.
So this is the problem. You cannot take any random surface. Understood? If you will take the any random surface, you will just stuck up here, that you will not be able to find this theta angle.
Yeah.
Okay, so this is the problem. So for to rectify this problem, what we are now going to learn here is that what kind of surface we can take for to apply this. Is this clear to you?
Yeah.
Okay, but remember this, that while calculating the flux, area is not required. While calculating phi e, do you require the area?
No.
No, that means phi e do not depend over the area. Do you agree?
Yes.
Yes, you should write it over here, that electric flux, it do not depend over area. Is this clear to you? Because what is going to happen in the future, if I'll ask you that phi, what is phi e, you will say E dot A. And if I ask you that do phi e depends over the area, you will say yes. But the reason, but as we had seen here, that phi e do not depend over the area. Okay,
Yeah.
it
Yeah.
only depends upon that how much charge is enclosed inside the particular surface. Okay, is this clear to you?
Yes.
Okay, so for to apply this particular formula, what is required here is we need to take a special area. We are confirmed about that. So what we'll do, we'll name that particular area to be Gaussian surface. Gaussian surface. Understood?
Yes.
So we are going to see that what this special surface is. and what should be the thing that should satisfy this particular, what are the conditions that is required for to uh, do that complete analysis. Okay,
Okay.
we are going to see the Gaussian surface. Okay, is this clear to you?
Yeah.
Or I have some questions also with me. Should I give you some questions over here?
Yeah.
Okay, first of all, see what is it is a closed loop. Just write it over here, and then I think I'll give you some questions. It is a closed loop. Okay, symmetrical. It should be symmetrical and three-dimensional. See, I'll give you the complete thing that is required for this particular Gaussian surface. See, uh, see now look at here. We are calculate what where we had stuck. We had stuck for E dot dA only for in the LHS part. Yes or no? Yes
Mm.
or no?
Yes.
We
Yes.
are stuck for calculating E dot dA only.
Yes.
This was the part. And what does this E dot dA comes out to be if we open this up?
E, E
E
into A cos theta.
dA into cos theta. Is this okay? So see,
Yes.
whenever you will choose the Gaussian surface, always remember this, that either the first thing, what is note, choose Gaussian surface in such a way that E becomes, see how you have to calculate it. See, tell me one thing, that if theta is 0, so can you calculate this expression easily?
Yeah. Will be
Uh,
E into
E
D.
dot dA, that's it. And if theta is 90 degree, what will be then? Phi E.
Mm.
What is the value of cos 90?
0.
That is 0. So do you believe that phi will comes out to be 0?
Yes.
So always take the Gaussian surface in such a way that electric field will become either perpendicular or parallel with the area vector.
Perpendicular.
Area vector or parallel to area vector. Understood? Is this clear to you?
Yeah.
Okay. Now, you will always see that while doing the selection for the Gaussian surface, I'll always satisfy these two conditions. Either the electric field will become parallel with the surface or it will become perpendicular to the surface. Is this clear to
Okay.
you?
Yeah.
Now see, suppose let us take a question. Okay, let us take an example here. Calculate E due to a point charge at a distance r. Okay. Now tell me one thing, that suppose what is happening here, that I had taken a small charge Q kept here. Understood? Yes or no?
Yeah.
And if I need to know about the magnitude of electric field at a distance, let's say r, at a distance r. So what it will be? If I need to know about the electric field at a distance r, so what it will be? What is the electric field at a distance r due to a point charge?
KQ square by R.
Kq by r square. Yes, you are right.
KQ
Okay,
by R
and
square.
it is kq by r square. Now we'll calculate it using the Gauss law. How will we do so? Take a Gaussian surface. But what the Gaussian surface should be? I'll take the Gaussian surface here to be sphere. I'll take this sphere to be the Gaussian surface, and I'll keep this point charge at the center of this surface. I'll take this point charge at the center of the surface. I'm taking the Gaussian surface. What the Gaussian surface I'm taking here? A sphere
Good.
of radius r. Understood? So do you believe that this time the electric field will be perpendicular with the surface? Do you agree?
Yeah, yes.
It will be perpendicular to the surface
Perpendicular.
always. That means the area vector and the electric field will be pointing along the same direction. Yes or no? Yes
Yes.
or no?
It's in the same way.
Area
Yes.
vector is always
Same way.
perpendicular to the surface. So it will be somewhat in same direction. So what will be the cos theta here? Theta will be equal to
1. I mean, theta will be
theta will be equal to
equal to 0.
0. What is this
0.
theta? This theta is the angle between E and A, and more specifically this small dA. Yes or no?
Yes.
Now we don't know about E. Let us consider that we don't know about the electric field, that what it is, and we are going to calculate it. We don't know. Let's say E is kq by r square, but we don't know about it. We will calculate it over here. So what is required here is that do you agree that this electric field will be everywhere over this surface? Yes or no?
Yes.
And there will be many. There will be many. Yes or no?
Yes.
Okay. Okay. Understood. But
Yes.
do you agree, due to the symmetry, the electric field at a distance, at every distance will be same?
Yeah.
Okay, that will be same because it is at a equal distance r. So if I calculate the electric field, what will I get? I'll get that E dot small dA1 area. Let's say we are calculating it over a small area dA1, and we are calculating it over again dA2. This is over dA3, and so on. So what will I get? If I do E dot dA, as cos theta is 0, so for to calculate E dot dA, this will become E into dA only. Yes or no?
Yes.
Because theta is
Yes.
0 here. So E dot dA, E into dA1, E into dA2 plus E into dA3. and so on. It will keep on going till E into DAN. Yes or no?
Yes.
And that will be equal to Q enclosed divided by epsilon naught.
Yes.
What is this Q enclosed equal to? Do you agree that this is nothing but Q? Yes or no?
Yes.
How much charge is enclosed inside this surface? That is Q only.
Yeah, Q only. Yeah. Okay.
So Q enclosed will be Q only divided by
Yes.
epsilon naught. And in the above expression, do you agree that E can be taken as common?
Yes. Yes. You can.
We can take it. Now tell me that dA1 plus dA2 plus dA3 and so on till dAn. Do you agree that the sum of all these surfaces will be nothing but the surface area of the sphere? This is all the small area over the sphere only.
Oh yes.
And that is nothing but 4 pi r square. The surface area of the sphere.
Yeah.
Yes or no? So what can you replace it with? 4 pi r square equals to q enclosed by epsilon naught. Understood?
Yeah.
So what it will be equal to? E equals to q divided by 4 pi epsilon naught into r square.
Oh,
Yes or no?
yeah. Yes.
Okay, because 4 pi r square is being divided in the downward part, I'll get this one. Okay. So now tell me one thing, that can I write it like 4 pi epsilon naught into q by r square?
Yes.
Okay, understood. This was q enclosed, that was equal to q only.
Yes.
Okay, this is q only. What this 4 pi 1 by 4 pi epsilon naught is equal to?
Yeah.
That is equal to k. So do you agree that E can be written as kq by r square?
Yes.
Is this the same thing that we had that we already know about?
Yes.
Kq
Yes.
by r square, and that we had calculated without knowing it about, just by using this particular expressions. Is this clear to you?
Yes.
So today's
Yes.
class, let it keep it till here only, and we had seen a lot of things today, so revise it definitely at your home. Okay,
Yeah.
with
Yeah.
don't come in the next class without revising it. You must revise it, only
I will.
then
Yeah.
you should join the next class. Is this okay?
Yes.
Okay,
That's okay.
I think keep it till here only. If you are having any doubts regarding this session, you must ask it, and or else we'll have the class next. I think in the next week. Okay.
Okay. Yeah, I have no doubts. I understood.
Okay. Okay. If no having no doubts, then you can leave now.
Thank you.